Well, howdy, physics sleuths and inquisitive souls, and welcome again to Dynamic Gravity. So today, there's a concept that confuses a lot of people, and that is, how is it possible that my math of dynamic gravity can be applied to Einstein's math or Newton's math, like as an augmented factor, like a modifier. And the reason why this is because essentially the gravitational constant and Coulombs constant are the same thing. They're just being applied in different ways. So let's dig into this. Show you what I'm talking about, guys. Right, so the gravitational constant, this is the whole thing that makes Newton's and Einstein's math work. Without this, they would have absolutely nothing at all, other than just fall off ratios of energy, nothing more. So, you clearly can see we got the gravitational constant, g, times the mass, object 1 and 2, divided by the radius squared. Okay? Now, the gravitational constant's units are, where are they at? Meter meter divided by kilogram divided by second squared. Now, this is almost m squared, meter squared, times a Newton. If we look at a Newton, the definition of a Newton, let's see, here we go. Yes. If I can make this a little bit bigger for you. Yes. So right here we have kilogram times m divided by s squared is a Newton. So if we look at this, this has got the divided by s squared, and it's got the m, two more m's. But the kilogram, instead of being times, this is divided by. So this is why it's not a Newton times m cubed. But it turns into that after you do the full equation. You times by, kilogram times kilogram. So yeah, just how the units work out and everything. But this number, which is an unfathomably small number, no, not that one. Yeah, right here. A very small number. It's basically just saying nothing more that for every kilogram of matter you have, this is how much force, or the modifier that it is going to put out per kilogram of gravity. How much force per kilogram of gravity, okay? So it's measured in weight and mass. Specifically, actually, yeah, I guess that's mass, not weight, mass. So, yeah, so it'd be gravitational force times mass. Now, if we look at Coulomb's constant, it's a little different. I mean, you notice the equation is pretty much exactly the same. You have the constant, Coulomb's constant, like we're Einstein, or Newton, it was the gravitational constant times m divided by r squared. Well, Coulomb, it's constant times charge strength times charge strength divided by r squared. And the units of a Coulomb's constant are a Newton times m squared. Funny how that m squared is still there, just like the gravitational constant has m squared once you take out one of these m's. Then times a Coulomb, which is the strength of the charge strength for an electron or proton. They're equal, just completely opposite. So there we go. It is basically Newton's times charge strength, right? And this is the reason why I can apply this into my theory of gravity, is because what Coulomb's constant is basically saying is, this is how much force is going to be put out in newtons, or not newtons, but how much multiplier, whatever, force times strength, charge strength, where the gravitational constant is instead kilogram. So this number, G, is measuring an effect that occurs per a certain amount of mass per kilogram, where coulombs is measuring an effect that occurs for a certain charge strength. All right? So let me go to my paper. This paper is in my my description. I have it linked, a link to it, and every video I publish on gravity. If you have not yet read it, I highly encourage you to download it and read it. It pretty much explains everything you need to know about gravity from start to finish in layman's terms. Very easy to get through, right? So what we've got here is, here are the two formulas, right? We got Newton's gravitational constant, whatever, and we got K, coulombs, okay? Now, I am able to apply my formula because what is actually going on here is when Coulomb is talking about measuring the charge between electrons or protons or whatever, he's doing it based upon the strength of the electron and the proton, right? Where Newton, when he calculates it, he's calculating the effect as it goes from a micro effect from, say, just like a particle or two, to a macro effect of, okay, now if we had all these particles that were, packed into standard matter, not a super celestial, those are totally different, but like in standard matter, like lead, gold, whatever, then it's going to be a certain strength per kilogram with standard matter, with how tightly standard matter can compact. And so that's really what G is. G is effectively, according to dynamic gravity anyways, which I'm the only one in town, guys, who can explain and calculate dark energy, dark matter. I don't need the Big Bang to get the origins of the universe. I can explain everything. I can calculate everything. All of Einstein's math is still good. I haven't derailed that. So if you're not believing me, and with dynamic gravity, who are you believing in? Why is the real question. Why are you believing them over me? What do they have that I don't? The answer is nothing. I have all the answers. They have all the conundrums and paradoxes and problems and issues that have to be fixed and resolved with exotic measures like machos and wimps and dark matter and dark energy and blah, 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 and mods. It goes on and on and on. All the different ways to try and fix Einstein's math. It's broken. It's broken. I fixed it. You're welcome. So that's the reason why these two are actually related. This one is when you're calculating gravity at a gravitational strength, like a charge, if we're talking about just an electron or proton, because that's what it is at those levels. Or if you're at a planet level, it is going to be the gravitational acceleration of the planet, little g, not big G, little g. Which, if I'm not mistaken, I'm pretty sure I got the formula for that here. Yeah, right here. There's the formula for little g, which, as you can see, involves g. So they're all related. This is why my math works, why I can do it. And if you're like, well, I don't believe your math works, cool story. Maybe you should read my paper first before you make such ridiculous statements. Here is a derivation I have working out of, from Newton's equation, and then working out to how my equation equals Newton's. And what happens is my equation, or my modifier, is equal to Newton's equation. Keep in mind, I got my modifier with this formula right here. This is my final formula right here. for mg to calculate all of the dark effects, anti-gravity effects, whatever you want to do it. Yeah, so Coulombs constant times the gravitational acceleration of your big and small celestial objects divided by the radius squared. And then you got to times it by a ratio of the small gravitational object's gravity divided by the larger one. Otherwise, you get really funky things going on with the math. It doesn't hold up very well on a micro level if you don't have this ratio. So this is a very important part, and it ultimately just, these two will cancel out, and then eventually what you just have is g1 times g1 divided by r squared times k. It's pretty much what it works out to be. But the reason why I can do this, the reason why I can apply this to Newton or Einstein's math, even though this doesn't have, g in it, the gravitational constant at all, is like I said, because g is related to g right here, as you can see, and k, the constant, is essentially just g, only on a scale of when you're looking at the system as a whole and not just calculating the summation of kilogram blocks of matter into that system. Okay, that's kind of a hard concept to understand, but that's what it is. K is when you're calculating gravity from gravity strength. G is when you're calculating as a summation of kilograms compiled together to form an object or whatever you have going. So there we go. I hope this explains everything. I highly recommend you download and look at my paper that I wrote on my theory of gravity. It explains everything. And I assure you, whatever questions you have, the answers are in there. I was very meticulous trying to explain as much as I can about my theory of gravity, crammed in like 5 short pages. So, yeah, that's basically the relationship between Coulomb's constant K and Newton's gravitational constant G. They are measuring, or they are constants of the same force, but just when you're going to calculate it in different ways, because you're trying to get a different effect, or you're trying to see a different part of the relationship of gravity, whether you're measuring just the attractive pull or the entire system, which is when you'd want to use the entire system, like I say, gravity, gravitational acceleration, G, with Coulomb's constants, when you're looking at the entire system as a whole, and you want to see the attractive gravity with the anti-gravity and calculate those together and see how they offset each other and what your total answer is. I hope that explains everything. Read my paper if you haven't already. Do yourself a favor. And I wish you all a good day, and I will see you in the next one. Adios.
Like, subscribe, submit.